Welcome to today's webinar, Do's and Don'ts of HSS. My name is Anna Finley with Civil and Structural Engineer Media. Thank you for joining today's webinar, which is sponsored by the Steel Tube Institute. Before we begin today's presentation, first some general information about the webinar and the GoToWebinar platform. The views of the speakers and organizations participating in this webinar are their own and do not necessarily reflect those of Civil and Structural Engineer Media or its publisher, Zweig Group. If you have any technical difficulties while viewing the webinar, please submit questions or a brief explanation of your technical problem using the Questions tab on the GoToWebinar control panel, and I will assist you. During the webinar, you can also submit questions to our speakers using the same Questions tab. Submit your questions at any time and we will try to answer as many as we can during the live Q&A session at the end of the webinar. Zweig Group encourages group learning for our events. If you are viewing the live webinar with a group on one registered person's computer, that person must complete and submit the multiple viewer registration form in order for everyone to earn a credit. Download the multiple viewer registration form in the Handouts tab on the control panel. Submission instructions are on the form. Viewers of archived webinars must pass a quiz in order to download a certificate of completion. Today's speaker is Beth Suminski. Beth has worked for 25 years as a structural engineer in the fields of consulting, engineering, software, and continuing education. During her first few years, her experiences in construction defect litigation cemented her understanding of how and how not to design a structure. She spent the following years as a practicing consulting engineer in San Diego and later as a director of structural software sales and development with Bentley. In her current position with Force, she continues to pursue both the design and educational aspects of structural engineering. Beth is a licensed PE and SE in California and a licensed PE in Arkansas. Beth will begin today's presentation.
Hello, everyone. I'm going to get my slides up on the screen now. And thank you, Anna, for the introduction. As she said, we are with the Steel Tube Institute, and we are happy to be with you today presenting Do's and Don'ts of HSS, hosted by Civil and Structural Engineer Magazine. My name is Beth Suminski, and let's get started today. We have just one more page of kind of administrative items before we go. Anna covered some of this already, but the webinar does accredit the registered attendee 1 PDH for the hour. You must complete the poll question, which is about halfway through the presentation, and attend the entire webinar today to receive a certificate. Site registration was not offered for a free webinar, but you do have the option to write down everyone who participated in your site on the form that is available from the downloads. And those registered in Florida, Maryland, North Carolina, or New York are required to complete a quiz to obtain your certificate. After the webinar, the quiz link will be emailed to you and it must be completed within 24 hours of the conclusion of the webinar. We encourage you to visit our website and take advantage of the valuable information we have for you there. We will be looking at a lot of that information throughout the course of today's webinar. Over the years, the Steel Tube Institute has fielded thousands of inquiries about the proper specification and design of HSS members and their connections. So we have selected a few of our favorite do's and don'ts and we'll share them throughout the course of the webinar. While none are as obvious as the cartoon you see here, which would be don't catch your pants on fire, we think you will find them equally as useful. Here are just a few of the learning objectives we will cover today. Do understand the subtleties between available material specifications. Don't always rely on the full length of your weld. Do know how to avoid end distance reductions or know how to apply them. Don't minimize your wall thickness. Lightest is not always cheapest. Do check availability of shapes and materials using STI's capability tool, which we will discuss. Don't over tighten bolts if you're using through bolts. And we'll talk about other common connection issues and many, many more. The way we've laid out the webinar today is that the first half will be devoted to sharing our real-world HSS practical do's and don'ts. We will go through these in a checklist style format. Then we will continue with a section devoted to how and when to best use HSS as part of the big picture of steel construction. And we will wrap up with a handy summary table to help you as you design your next HSS project. So let's jump in. First, we'll look at practical and technical do's and don'ts, things that you need to use in your everyday design practice. We'll start with material grade, and specifically A500. A500 is the most commonly used HSS material grade. And when you are specifying A500, do specify grade C. Don't specify grade A. It's important to note that in the past, A500 had 4 different grades, A, B, C, and D. In the beginning of 2021, grade A was eliminated from the A500 spec because it wasn't being produced and had a low yield strength. So that left grades B, C, and D. However, you should be aware that in the US, A500 carries dual certification. What that means is that for the past 20-ish years or so, all domestically produced A500 material has met both grade B and grade C specifications. So a lot of engineers are still specifying grade B as a minimum because it had a lower yield strength and we are trying to be conservative. But we are recommending not to specify grade B because you're getting grade C anyway. And you can see the material test report here that shows dual certification in this highlighted yellow area. It specifies that it's certified to both grade B and C. So you're going to get grade C steel even if you specify grade B. So it's best practice for engineers to use the higher grade C yield strength. And take a look at your general notes and see if you are still carrying grade B, and if so, you can switch that to grade C. Now, I mentioned that in 2021, grade A was eliminated from A500. There were other significant updates to ASTM A500 in 2021. So you do need to be aware of those updates. So one of the major updates is that yield strengths were upgraded, if you'd like to think of it that way. Yield strengths for round HSS used to be slightly lower than yield strengths for squares and rectangles. But now with this latest upgrade, they are the same. So you can see that for grade C, the round structural tubing has the 50 KSI yield strength, which is the same as the rectangular structural tubing at the 50 KSI yield strength. So now everything is 50. If you are still specifying 46 KSI for your round tubes, that is no longer the case. It's a great advantage. Take advantage of whatever extra yield strength you can get. Also, the maximum wall thickness increased from 7/8 inch to 1 inch thick, and the maximum periphery increased to 88 inches. So that means that we will see larger HSS shapes available domestically here in the US. You may have heard those referred to as jumbo HSS. So our largest square shape doesn't change at 22 by 22, but we can now specify up to 28 inches round, and rectangular shapes can increase up to 34 by 10. So the other thing I want to talk about in material grades are other structural as well as non-structural ASTMs. So let's talk a little bit about A500 round again. If you have a round shape, we recommend that you do specify A500 for that round shape. We get the question a lot, well, can I specify A53 pipe as a structural round shape? You can. We do recommend that you specify A500 round, but don't overlook the fact that A53 or even A513 is sometimes specified as a round shape or substituted for A500. So if you do get that request for a substitution, just be aware that the A53 and the A513 specs don't have a minimum yield strength, or it's lower than what we would see with A500. So if you are having that substituted, make sure that you check the material report for the material that's actually being substituted and verify that it has the yield strength that you are looking for. So do specify a minimum yield and check for a minimum yield if you're substituting A53 or A513 for A500. Another reason that A500 is typically specified for structural uses is that A53 is often more expensive, and that is because it has to go through testing to make sure it can handle pressure. The application for A53 is often for pipes, so it's a pipe spec. So it has to be able to handle the pressure. It has to go through the testing to make sure it can handle that pressure. A53 is also coated, so you're paying for that as well. And if you need to weld to that pipe, you would need to remove the coat, and that comes at a cost as well. So if you have round shapes you need to design for, we recommend specifying A500 rounds, or just being aware of the differences if you do utilize A53 or A513. Another material grade that was discussed quite a bit in the last couple of years is A1085. A1085 has a few differences from A500, but unfortunately the availability for that material has not come into production as much as we expected. So make sure that if you are utilizing A1085 that you check that it is available before you specify it. And another thing to be aware of is that STI has a capability tool. You can see the link for that at the bottom of this slide. That tool will tell you which of the Steel Tube Institute's member producers are capable of producing which sizes and material specifications. Next, we'll move into wall thicknesses for design. Now, you may or may not be aware of this, but the A500 spec allows a plus or minus 10% variation in wall thickness. So a savvy producer would create a shape on the lower end of that spec requirement. And so you might end up with a wall thickness that's 10% less than the nominal wall thickness. And so because it can be produced with such a large swing in tolerances, AISC accounted for that by reducing the nominal or the design thickness, to 0.93 times that nominal thickness. Now, if you are looking at the material properties in the AISC manual, it does assume A500, and you will see a design thickness listed that is already reduced. So it's already the 0.93 times the T nominal. So for example, if you had a tube that was a 4 by 4 by 1/4, the nominal wall thickness would be 1/4 inch, but the design wall thickness would be 0.3 times that, so you're looking at closer to 0.23 inches thickness for your design. So as you can see here, the wall of that needs to be taken down a little bit in your design calculations, or just ensure that whatever table you're looking at already is using those values for the design wall thickness. Now, in the Steel Tube Institute's design manual, we have all of these properties already listed out for you, so you can take a look at that as well. Now, if you're utilizing A1085, which we just talked about as potentially having more limited availability, you would not have to reduce this wall thickness. The spec for A1085 has tighter tolerances, So we don't require, or the steel design, AISC doesn't require that wall thickness to be reduced. So because there are these different variations, we have those tables in the STI Design Manual Volume 1, and it includes all the appropriate section properties for A500, A1085, and even A1065. So the design thickness for a 1085 would be equal to the nominal wall thickness. Now let's talk about choosing the wall thickness in your design. We need to remember to perform connection checks when selecting your HSS member in the design process. So do consider your connections during the member design. I know a lot of engineers are designing the main member and then delegating the connection design down the road. But at the step that we're picking our member, we need to at least consider the loads that are going to be imparted by the connection on the wall of your member. So if we just use our nice software design tool and create the very thinnest wall possible for our design, we may end up with connections down the road. So don't assume that the lightest HSS is going to end up being the cheapest option with HSS, because connections do come into play in that calculation. And the local strength at flexible HSS walls may control. Just be aware of that, and there are options for checking your wall for your connection forces without actually having to go through the entire connection design. And those are some tools on the Steel Tube Institute website as well. And along these lines, don't be fooled by tension-only designs. If your member is only loaded in tension, you will likely get away with a very thin wall, but that high slenderness ratio will likely result in reinforced connections down the road. And those fabrication costs factor heavily into the finished structure cost. So that flexible wall that we just saw, that's just one of the ways that an HSS section can fail, and that is called a limit state. So do become familiar with HSS limit states. They include punching, local yielding, local buckling, plastification, and anyone new to designing structural steel connections involving HSS members may be surprised or a bit overwhelmed by all of these various limit states and all of the associated equations listed in AISC Steel Spec Chapter K or in the manual Part 9. So just to note that these limit states have to be considered when connecting to an HSS, but they also have to be considered when connecting to the web of a wide flange member, and those two things are very similar. We don't want to use the outdated 2010 Chapter K tables. AISC 360-2016 removed many prescriptive connection design tables that were in 2010 Chapter K because they wanted to refer everything back to the section in the code as if you were designing to the web of a wide flange. It's the same process, so they wanted to use all the same equations and not potentially have duplicate material that doesn't match. But during that change with those tables that were removed in 2010 and now referring back to formulas in 2016, there became a need for a roadmap or a cheat sheet to go between the two and to help engineers when you're looking at the wall and the limit state of an HSS. So we created the Steel Tube Institute limit state tables. And like I said, this is a cheat sheet that helps you understand each limit state that is required to be checked for your connection types. So we want to make sure that you're moving away from the outdated 2010 Chapter K tables and using 2016, and the STI limit state table is a great way to do that. Another don't that we want to point out here is don't assume that your connection software checks all of the limit states. Now, what we recommend is that you do a verification example up front, because there may be some limit states that aren't incorporated yet into your connection design software. So just a heads up that that could be something that is overlooked. To reiterate and sum up that limit state table discussion, we're going away from 36010, which is the red manual that you see here, where most of the information about HSS was contained in Chapter K tables that were very prescriptive. They were unique to the spec. The content was repetitive from where it was listed elsewhere in the code. And there were often some limits of applicability that you needed to ensure were met to utilize those tables. What we're going to is Chapter K in 36016, which is really just adding on to information that's in Chapter J. It's additional requirements. And this way the code is very consistent, there's no duplication, and a lot of these limits of applicability were removed because we're not looking at tables anymore, we're looking at actual formulas. So per AISC 36016, the available strength of connections shall be determined based on applicable limit states from Chapter J. And to help us understand visually what those limit states are, I always like to show these slides. On the left is punching. It can occur in both tension and compression when we're connecting to the face of an HSS cord. The image to the right is plastification. The tube wall is very flexible as it spans between the side walls, and so it's deforming under concentrated load, forming yield lines at that HSS connecting face. Some additional limit states are sidewall failure, which can take the form of yielding, crippling, or buckling. And then lastly, we can have local yielding due to uneven distribution of load. And that basically means that the cord member is more stiff than the branch that's framing into it. And so you can see premature failure of the branch members due to that uneven stiffness. So these are just some of the limit states to check when designing with HSS connections. With all connection approaches, we recommend, and you must check all applicable limit states for your connection to determine which one is governing. So a second ago, we talked about limits of applicability, and although many of these have been removed from the code in an effort to align more with Chapter J, there are still some limits of applicability, or LOA, to become familiar with. This is because they govern the use of the prescriptive AISC equations that are still included in the code. There are still some in there. A lot of them are for round shapes because you don't have that equivalent web of a wide flange member. And so the round is addressed slightly differently and still does have quite a few tables in it. So do check the limits of applicability as a first step in designing HSS connections. You can refer to the limit state tables that we just talked about. However, if you are finding a prescriptive equation in the code that does have some limits of applicability, don't apply those equations if your connection falls outside of the limits of applicability. It's a pretty common sense approach, but a lot of times when we see those tables and our connection doesn't fit into the limit, we still want to use it and think, oh, we'll just go ahead and use that. But that should not be done. In that case, then you need to go back to formulas or some kind of testing approach. One of the limits of applicability is end distance. So we will talk a little bit now about end distance provisions. When a connection is near the end of an HSS member, there may not be adequate length to develop a traditional yield line pattern, and that means that the joint may not be able to develop its full connection capacity. So do be aware that connection available strengths in Chapter K must meet end distance limits of applicability. And you can see the formulas that are taken from Chapter K here for both rectangular or circular sections. If you don't meet that end distance requirement, then you do need to apply a reduction to your connection capacity where the end distance LOA is not met. A conservative reduction of 50% is typical. And if you don't want to reduce your connection capacity by 50%, you could always use a cap or an end plate to waive that end distance limit of applicability. And we have an image of that here so you can visualize what it is that I'm talking about. So our main member, the cord, is our horizontal member here, and then we have our branch member framing into that. And you can see how close it is to the end of the main cord member. This connection would not meet the end distance requirements. So in this particular instance, you would need to reduce your capacity by 50%. Or if you did add a cap plate to seal off the end of that tube, you would not need to apply your 50% reduction. So moving on to effective width for rectangular HSS. We saw that flexible wall. You can see it's distorting here a little bit. That's not under the heaviest loading yet, but eventually that wall will bow down and flex under this point load. So we saw that flexible wall, and the flexibility of that wall results in what is called the effective width phenomenon for square or rectangular HSS sections. So as you can see in this image here, where the HSS wall is spanning across and connecting to the side walls of the HSS, it's going to be much more flexible in the middle, and then it's stiffer at the ends where it's connected. So that causes a non-uniform distribution of forces. So in many instances, you cannot rely on the full width of anything connected to that face. Now the code is very specific in saying this is for connection of plates or branch members that are perpendicular to the longitudinal axis of the HSS. And so in those situations, there's a formula to calculate the effective width. So don't rely on the full width of plates or branches perpendicular to the longitudinal HSS axis. You need to calculate the effective width. And that formula is shown here on the screen, and that is taken from the code Chapter K. And that B sub E is the effective width. And once you calculate that effective width, then you use that value to calculate other reduced parameters. So for example, if you had a weld across the face of your HSS, you would need to use an effective weld length, and that is per table K 5.1, and you can see the equation for your effective weld length there. So because the force is non-uniform, the force in the weld is also non-uniform, and you cannot rely on the full length of your weld. And again, this is only going to be for connections that are across the face, that are transverse across the HSS. Okay, a little bit more on welding to HSS. There's a pretty commonly used directionality factor of 1.5 that is applied to fillet weld capacities. And it's an increase of 1.5 that you can take when a load is applied transverse or perpendicular to fillet welds. And you need to apply that directionality factor correctly for HSS, which means in most cases, you don't get to use that 1.5 increase for most HSS connections. And we'll go through the reasoning why in the next few slides. There is another instead of an increase, there is a limitation for fillet welds, for welds at the edges of members, and that actually would not apply to a fillet weld around a HSS at a base plate. And that is because you're not welding at the actual end of the plate where you might burn off that material. And we'll take a look at this in a little more detail on the next few slides. But that particular limitation of a max fillet to be T minus 1/16 inch is not applicable at HSS base plates. But talking about the directional strength increase factor first. Section J 2.4b permits the use of this directional increase for certain fillet welds, blah, 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 blah. This is based on research on lap splice connections loaded in shear, and it's used in a lot of other applications other than that. So the research found that the 1.5 factor, when applied to a single-sided weld, was not applicable. So single-sided welds to an HSS wall, you can see here, they are partially unrestrained. That weld will be loaded eccentrically and it will try to open up the weld root. So with a single-sided weld to an HSS, when they're in tension, they're partially restrained, and that's going to make that 1.5 increase not conservative. So in this instance, this is when it's used most, probably if you're looking at an HSS to a base plate. So you would not want to use that 1.5 increase at that instance. Now, there is less restraint if that is utilized on a round HSS. So the effect is much more severe on rectangles than rounds. So that 1.5 increase should not be used for rectangular HSS in tension to base or cap plates, but it's okay for round HSS. And the 1.5 increase should not be used for effective welds with that K5 formula that we looked at to rectangular HSS connections, that is on transverse plates going across the base of it. Now, if your column is in compression, then you could use that 1.5 increase, although at that point you probably don't really have a lot of load that you're resisting for a column connection and compression to a base plate. And then to summarize, do use the 1.5 increase, or you can use it if you have a round HSS in tension, but don't use the 1.5 increase if you have a rectangular HSS in tension, or if you are looking at an effective weld length in K5. We have a nice article about that on our website as well. Now, this was the second don't that I had on a slide a couple back, where we don't have to apply the limitation of T minus 1/16 inch at the edge, at a weld applied at the edge of a member. And the reason that does not apply is that you can see here in this image per the code that really we're talking about a weld at the end of a member, and that could burn off some of your member thickness, so, or melt it off. And so the T minus 1/16 inch limitation was to ensure that you have the proper weld throat, that you have enough material to attach to. However, if you're welding at the end of an HSS to a base plate, there's really no way that you're going to be melting that edge or making it thinner than we think it is. So that particular limitation of T minus 1/16 inch does not apply at an HSS base plate. So we have one instance where the 1.5 increase can not be used, and then we have one instance where a limitation does not need to be used. So one's kind of a limitation and one is the removal of a limitation. We're going to summarize all this in a table at the end, but that one is two different things that we're talking about for weld limitations. Now, the other type of connection we want to address is bolting to HSS. So bolting to HSS can be difficult in the same way that we can't achieve an easy weld access inside a section. It would similarly be a challenge to tighten bolts inside a closed shape. So bolting is difficult due to the closed nature of an HSS section. It's not impossible, but it can be difficult. If you definitely need to do it, then you don't forget your access holes, because there would be, unless you're at the end of a section, there would be no way to get your tool in there to tighten the nut on your bolt. Now, if you're not using traditional bolts and you want to use through bolts, well, we actually recommend that you don't through bolt if possible. It is difficult to install. You can imagine trying to get that bolt through the hole on the near side and the hole on the far side. You can also imagine that the length to get through that entire section may exceed a stock bolt length. And then if you're tightening down with a through bolt, you could deform the sides, the walls of your HSS. So don't over tighten through bolts. If you're using them, only tighten them snug tight. Now, if you have to use through bolts, we actually recommend that you should reinforce your HSS if you're using through bolts, and that way you could tension them if necessary. There are also alternatives, so we do recommend alternatives such as Nelson studs or blind bolts as an option to through bolts. Here's a couple of images here. If you were tightening this through bolt, you have this potential distortion of the HSS wall. But on the left, you could see how you would want to properly through bolt. You would put a sleeve inside the tube so that you would be able to get that bolt through and tighten it down without this distortion of the HSS wall. And then this little image here is just a trailer hitch that's something more real world that we might be able to imagine how hard it is to get that pin through. And then in the field with something even much larger, it becomes even more difficult. Okay, so moving into a little section on truss type connections. So when we talk about truss type connections, we're usually talking about cords with web members. And the way we usually design it is based on the connection types. And so something like a K or a T. Do designate that connection type, the K, the T, the Y, on the force transfer in your connection. Don't designate your truss connection based solely on what it looks like. And don't just assume that because it looks like a K, it's a K, or it looks like a T, it's a T. There are actually rules to these letter connection types. And you can see a couple of the images here. A K, which would also be an N connection, has certain requirements about how much of the load is equilibrated by other branch members, or that is transferred across the cord for the Y and the T members, or the X or cross member where that load is transferred through the cord member. So you have to look at the actual forces in your cord and your branches and see how that load is being transferred before you designate your truss type connection. So it's based on the method of force transfer in the connection, not just on the physical appearance of the connection, although that often does end up being the same thing. Our last set of practical do's and don'ts to use are the HSS Design Resources. So we do recommend that you use these resources. All the things that I've just discussed can be found on our website, the HSS Design Manuals, Limit State Tables, Capability Tool, HSS Connects, e-news, Resource Library, Webinars on Demand, and the Library of Articles. What we don't recommend is that you continue to use old general notes that may be outdated, old specifications that may be outdated, such as ASTM A500B, when we now have the dual cert of the B and the C, or just because, quote, we've always done it this way. HSS has come a long way in research and code changes in the last 5 or 10 years, so there is a lot of information out there for your use that's going to make your design much more efficient than just doing it the way that you've always done it. So we'll take a look at those resources, just flipping through them here. The HSS design manuals, these are available for purchase on our website. The limit state tables, this is just an overview of what some of them look like. This is the T and Y connection, and then we have a 360-10 column, a 360-16 column, and all of the necessary formulas to perform the checks for each of the limit states. And this is much, much bigger. This is just a snippet of it, but we have a lot of information in these limit state tables that can be downloaded from our website. The capability tool, we talked earlier also about making sure that what you specify is actually available, especially when it comes to materials. So this tool was created for STI so that you, as the engineer, can determine what is the most readily available or whether something is actually available now in production. So you can go in and select your shape and a range of dimensions and then the material grade, and you'll see the results in a table for different wall thicknesses. And if you get a solid dot, then these are the STI member producers who are rolling that section regularly. If you see a hollow dot, you would see the producers who can create that shape, but it would probably not be, it would only be on demand. And then if there's a dash in there, it's not produced. So this is a great tool, especially again with software. It picks the most economical or the lightest shape, but that shape may not actually be something that's readily available. So it's always good practice to go and check what's out there and available today. Another tool on our website is HSS Connects. We talked about how the wall of the HSS, when you design for the connection to that wall, may govern the design. So if you know the forces from your connection, you should be looking at your wall to make sure it is adequate to resist those forces. So HSS Connects is on our website. It used to require a membership, but now it's free to anyone. So you can go in and plug in your connection type and then the loads on the wall of your tube, and it will tell you if that wall is adequate. Now it doesn't go through and perform the entire connection check. It's not going to tell you how many bolts you need or what your weld size is or anything like that, but it will tell you if your main member is adequate for the forces being imparted on it. So now we're coming to our polling question, and just a reminder that we do expect you to reply to the poll in order to receive your PDH certificate. And please look behind your presentation. If you don't see it popping up, you may have to exit full screen in order to see that. So our poll question is, the engineer is required to check only one limit state per HSS connection design. And your choices are true or false. So we will leave that up here for a little bit and let everyone find the poll and then provide an answer. But so the question again, true or false, the engineer is required to check only one limit state per HSS connection design. Okay, so hopefully you all were able to choose an answer on the poll. We will go ahead and close that now. And then we will move into the second portion of our presentation. First, we looked at practical do's and don'ts. Now we're going to look at big picture do's and don'ts. And this section is devoted to how and when to best use HSS as part of the big picture of steel construction. We often hear that designers don't specify HSS because it's considered too expensive. It's almost like saying, well, we're going to use a pencil and a straight edge because a computer is too expensive. It's not just about the cost, it's about how you use the capabilities and efficiencies to know if it's worth the cost. So we want to focus on how HSS is beneficial, and there are a lot of benefits. It's excellent for columns. Its biaxial strength makes using HSS for corner columns a must. It has torsional superiority to open sections. It's great for curved members or exposed members in AESS or architecturally exposed structural steel. And we often see it used in unique and non-building structures because of all of those benefits listed above. So do recognize all these big picture benefits and don't default to the idea that HSS is expensive. It has a great, it's very efficient in weight to strength. So it has great capability for its weight. And we need to look at the overall fabricated project cost, not just the cost per ton. Sometimes when comparing a wide flange cost per pound to an HSS per pound, wide flange may or may not be less expensive. The market value, it'll fluctuate, but HSS will be more efficient per pound for axial loading. So we need to look at that overall fabricated cost, not just $1 per pound or $1 per ton. So reasons to use HSS for columns, they are more efficient, as I just mentioned, and that is primarily because there is no weak axis. So there's no loss of strength in that weak axis direction because there isn't one. And just for a quick numerical example here, if you had a 12-foot column and you're looking at a W12 by 58 versus an HSS 12 by 12 by 3/8, which are roughly the same weight per foot, that HSS section would have about 12% more capacity at the same weight per foot. We can also fill the HSS with concrete for more capacity. We recommend that you do use the jumbo HSS that are now becoming more readily available. It further increases your column capacity. We have squares up to 22 inches, rounds up to 28 inches, and rectangles up to 34 by 10 with wall thicknesses up to 1 inch. So do use those HSS columns for things like big box and warehouse stores. This is a Target store here, and you want as much of an open floor plan as possible. You want to spread out your columns as much as possible, so we need them to be efficient. The enclosed columns are good because they're cleaner, easier to maintain. They don't get the dust and dirt buildup as you would with an open shape. Another great thing to consider with HSS in the big picture is their biaxial strength. So do use HSS to reduce bracing, again, because there's no weak axis. If you're looking at, for example, a cord of a truss, that out of plane direction either may not need to be braced or braced less frequently than a member that would have a weak axis. This is a quick case study where we had some vertical trusses, and just by converting from a wide flange to an HSS option, we were able to reduce a lot of the weight and the number of pieces because of the reduction in out-of-plane bracing. Do use curved and architecturally exposed HSS. Round HSS are especially adaptable to almost anything that a designer can imagine. And when you do expose the HSS, their smooth appearance is very pleasing. Varied shapes are available between square, rectangular, and round sections. A thing to note is that not all exposed HSS needs to be specified as AESS, the architecturally exposed structural steel. When you specify AESS, then your member has to meet certain criteria, things like how visible certain imperfections are, or whether or not your weld needs to be ground smooth. And oftentimes you can get that nice and clean exposed look without actually specifying it as AESS. And so that would reduce some of the additional costs that would be incurred with a more restrictive AESS specification. Here's a couple of images. This is a structure called Allianz Field. It's home to the Minnesota soccer team. It was the AISC 2022 Ideas 2 award winner, and It has a transparent building skin. It's supported by round 18-inch diameter HSS. You can see how beautifully you can see through the skin and how it wraps around the round HSS. It drives the skin's complex geometry, and it is the supporting structure. And here are some images of that under construction. Each HSS piece was curved to its own single radius and then connected with end plate moment connections. This created a very complex look, but because each HSS section was only singly curved, it allowed for a very straightforward fabrication and construction process. HSS are often used for exposed exterior curtain walls as well. You can see here a picture of the SeaTac International Airport, and round HSS are being utilized, and also rectangular HSS at the girts. So when you're wanting to let in light, exposed HSS are a great choice that looks nice without blocking that light with unnecessary enclosures. Another image here, this is the Salvador Dali Museum in St. Pete's, Florida. In this case, rectangular HSS were used. This was a space frame supporting a free-form glazing system. Multi-story structures are also excellent uses of HSS. Oftentimes you see canopies supported by columns that are unbraced for their entire length, and they could be 2 or 3 stories tall. And this one was a 26-foot roof cantilever supported by 4 HSS sloped columns. They were exposed as architecturally exposed to steel. We didn't create the structure, but I do know that they also incorporated cast connects, forged steel castings to provide a really nice taper and pin connection at the top and bottom of each column. So canopies are also an excellent use for HSS. Here's another image of a canopy. This is from that Allianz field we looked at a moment ago. The compression elements of this cantilevered canopy are HSS sections. You can see that in the columns and brace struts there. Too fast. Another application where you would want to let light in without blocking it is in atriums. This is the Trans-Bay Transit Center. And this project used HSS, again, with casted connections from Cast Connects for a very seamless final look. HSS are excellent in non-building structures. They are so flexible, they can take on many, many unique shapes. In this instance, which is the Ballston Quarter pedestrian walkway in Arlington, Virginia, the bridge was needed to connect 2 buildings that were offset. So they created this very unique twist in the middle. It was a really interesting project. Not only does it twist, it's supported in the center and the sides cantilever. So that HSS frame provided the necessary rigidity to minimize deflection and bounce for pedestrians who were walking across that walkway. And of course, it just looks cool. And of course, HSS is great as exposed steel. We talked about that a little already. Great choice for AESS applications. It can be used not just for exterior applications, but for interior spaces as well. That brings us to our summary table. I don't expect you to read all of this right now, but we went through a lot of information, both on the practical side and on the big picture side, and I wanted to have that accessible to you in a easy to read format. So these are the do's and don'ts that we covered in the presentation today. Print them out, put them somewhere that the next time you're utilizing HSS on your next project, you can refer back to them. And remember to use HSS for all its advantages, and don't assume that HSS equals expensive. Those would be the 2 big takeaways that I would love for you to get from the presentation today. So with that, we're going to move into the Q&A portion. And it looks like we have about 5 minutes. I have a colleague with me on the webinar today. Kathleen, did we get any questions that came in? Would you like to jump in with those?
Thank you, Beth. Yes, we did get questions today. The first question that we received is ASTM A513 a pre-qualified base metal in the welding code AWS D1.1? And the answer is no. ASTM A513, which Beth had discussed, covers many of the very small tubular sections, oftentimes used for handrails and second miscellaneous steel components and such. That A513 is not on the list currently of pre-qualified base metals in AWSD 1.1. And for reference, that's table 3.1 in the AWS code. But this does not mean that we necessarily cannot weld to A513. It is still possible to weld to A513 steel if the welding procedure is suitable for the steel and for the service that is intended. Another few questions that have come up about whether or not slides will be made available. And yes, slides for today's session will be sent out after the webinar. We've also, and that will include that last slide on the do's and don'ts summary that summarizes the summary table of do's and don'ts. Those slides that you will receive an email form will include that slide. Another question that we received is, why hasn't ASTM A1085 become more popular? This is a great question. A1085 does have, so the advantages to it is that we can count on a larger wall thickness. We don't have to reduce our wall thickness, as Beth had mentioned, by 0.93. We can count on the full nominal thickness for HSS, and we can also use the same 50 KSI yield as we can for A500 grade C. The reason why it hasn't become more popular is that HSS is distributed slightly different than wide flange or angles or other steel, in that after HSS is manufactured by an HSS producer, it is then sent to a service center. There's sort of a middle distributor, and then that service center will send HSS to fabricators. So the service centers, domestic service centers in the United States don't always stock A1085 regularly, and not in all sizes that are available to be manufactured. And since it's not stocked in most service centers, it's best to check with an HSS producer to make sure that the shapes that you want to specify in your drawings are available. We recommend there is a capability tool on the website that Beth had mentioned, on the STI website, where you can see and check what A1085 sections are produced by which producers, Atlas or Nucor, Bull Moose, etc., and then can contact them directly, or you can send an inquiry to the Steel Tube Institute. On our website, we have a Contact Us page, and we recommend checking before submitting drawings for construction, and STI or any HSS producer can help to coordinate the availability of any A1085 material for you. Another question that we received is, where we have exterior columns, how do we address the concern of condensation water inside of the HSS? This is a detailing issue that we would recommend closing off the HSS section with by providing cap plates at any exposed ends of the HSS, just to avoid any infiltration of water into the member, which can cause corrosion over time. We also recommend providing weep holes at the lowest point of the HSS. So in an HSS column, close to the bottom or the base plate of that HSS. And then if it's a beam, at the underside of that HSS, or if it's a cantilevered, say canopy HSS beam, at close to the end, so the lowest point of the beam. There is some guidance out there to provide minimum diameter of 1/2 inch to for that weep hole. And if that member is exposed and galvanized, then that weep hole can also do some double duty for you, serving as a vent hole in the galvanizing process as well. There is an article on the STI website. If you go to our Steel Tube Institute website, the resource library, and search water drain holes, then you'll see an article to provide additional information for you. see. I do see another question. What supplemental specifications are required when we're using HSS as AESS? So this is a good question. There are 2 articles on the STI website that summarize AESS and all its considerations for HSS, and there is also a free recording for a webinar. It's what we were calling a webinars on demand, and I can try to email these links to these resources directly to you, but off the top of my head, when we have AESS, and depending on the category of AESS that you are trying to meet, there are different specifications we do need to keep in mind. The biggest one is weld seam, where you have, depending on the category of AESS that your project is in, that you may need to specify where the weld seam needs to be for HSS. Usually it is desired not to be exposed, and so that needs to be specified where the weld seam is to be placed and how the HSS is to be installed so that the weld seam is not visible. There's also grinding of that weld seam that is required, and but the additional specifications are provided on our website as well.
And Kathleen, is that document called the Code of Practice, or I can't remember exactly what it's called, but there's, sorry, I'm blanking on it, but I believe there is a—
Oh, the Code of Standard Practice. Yes, the Code of Standard Practice does list all the AESS categories, and we try to summarize specific to HSS what to do, what specifications are needed in 2 articles on our website. But yes, you're right, Beth. Thank you. And I think that's all that we have. Any other questions that we may have accidentally missed, we will work to email you directly. Thank you.
Thank you, Kathleen, for summarizing those. And as she said, the slides will be emailed to you in the follow-up email, so you will have access to all of this information. We hope that it was useful and that you will utilize HSS for your future projects. Don't hesitate to contact us if there are other questions.
Perfect. Thank you so much, Beth and Kathleen. As we finish, please make sure to download your certificate of completion now from the handouts tab in the control panel. A follow-up email will be sent to all attendees and will include the presentation slides, the webinar recording, and the certificate of completion. If you missed our note at the beginning and you're watching the live webinar with a group on one person's computer, please download the multiple viewer registration form, which is also under the handouts tab, and email it to me at afinley@zweiggroup.com. And thank you so much to Beth Suminski and Kathleen and everyone at the Steel Tube Institute for this presentation. And thank you everyone who joined us, and this ends today's webinar. Thank you all so much.